Cancer cells are notorious for hijacking metabolic pathways to support their unchecked proliferation, and among the most essential molecules fueling this process is NAD, a coenzyme that plays a central role in glycolysis, the TCA cycle, oxidative phosphorylation, DNA repair, and redox balance. As a result, the manipulation of NAD metabolism has become a hotbed of oncology research. Yet, much of this focus centers around targeting NAD, biosynthesis enzymes like NEMPT, or exploring salvage pathway intermediates like NR and NMN. Largely overlooked in this arena is niacin. Despite its straightforward entry into NAD, metabolism via the Price-Handler pathway, and its long-standing history as a potent NAD enhancer. The possibility that niacin could serve as a metabolic lever in cancer, either to support normal tissue resilience or to selectively stress tumor cells, remains vastly underexplored and potentially therapeutically significant. To understand niacin's untapped oncologic potential, it's essential to consider the metabolic bottlenecks that arise in cancer. Tumors often become dependent on the NMPT-mediated salvage pathway, using nicotinamide, NEM, as a key NAD precursor, converting it to NMN and then to NAD. This dependency has made NMPT inhibition a proposed anti-cancer strategy. By blocking the tumor's NAD recycling route, researchers aim to trigger energy collapse and cell death. However, this strategy risks harming normal cells too, which also rely, though to a lesser extent, on NAMPT for NAD maintenance. What's often missing from this discussion is that niacin bypasses NAMPT entirely, entering through the Price-Handler pathway via NAPRT, nicotinic acid phosphorybosal transferase. This alternate route is not just a biochemical curiosity, it may be a therapeutic exploit. Many aggressive cancers, such as glioblastoma, pancreatic ductal adenocarcinoma, and certain leukemias, downregulate or silence NAPRT expression to avoid competition with salvage pathways or to escape regulatory NAD pools that would slow proliferation. In such tumors, niacin becomes ineffective at raising NAD within cancer cells but can still support healthy NAPRT competence surrounding tissues. This has led to a provocative concept: synthetic lethality via niacin rescue. When used alongside NAMPT inhibitors, niacin can potentially rescue normal cells by providing them with NAD via NAPRT, while tumor cells lacking NAPRT remain vulnerable and NAD depleted. This differential pathway access could enable a therapeutic window where niacin acts protectively for host tissues without aiding the tumor, a rare, elegant example of metabolic selectivity. In tumors that do express NAPRT, the picture becomes more nuanced. Here, niacin could, in theory, bolster NAD production and fuel tumor energetics. But even this scenario may not be universally harmful. For certain types of cancer therapy, such as genotoxic agents, e.g. radiation or chemotherapy, cells require NAD to activate PRP enzymes for DNA repair. By transiently boosting NAD through niacin administration, one could augment DNA repair in healthy cells, improving tissue recovery and tolerance to therapy. There is even some evidence from preclinical models that niacin can protect hematopoietic stem cells from chemotoxicity without protecting the tumor. The specificity again depends on the differential metabolic capacity of tumor versus normal cells. Adding another layer of interest is niacin's interaction with GPR109A, a high-affinity receptor expressed in various epithelial and immune cells. This receptor, which mediates niacin's anti-inflammatory effects, has also been found in certain colon and breast cancer cells, where its activation may promote differentiation, apoptosis, or growth arrest. In colon cancer models, GPR109A expression is often downregulated, but when reactivated by either epigenetic drugs or niacin, tumor suppression has been observed. This suggests niacin may have receptor-mediated anti-tumor activity in select cancers, independent of its NAD boosting role. Despite these promising leads, niacin has remained on the sidelines of cancer research, possibly due to its lack of patentability, historic baggage as a vitamin, or concerns about fueling tumor metabolism. Yet the story is far from black and white. Tumor reliance on NAD is real, but context-specific. Some tumors may suffer from NAD overload, others from deprivation. Some may use salvage pathways exclusively, while others have access to both salvage and price handler routes. The role of niacin must be interpreted within this landscape of NAD pathway heterogeneity, not through one-size-fits-all assumptions. Importantly, niacin is safe, inexpensive, and already clinically approved, making it a practical candidate for repurposing in cancer trials, whether as a NAD support for healthy tissue, an adjuvant to NAD targeting inhibitors, or a modulator of immune and inflammatory tone in the tumor microenvironment. Its ability to induce differentiation in myeloid cells, regulate sirtuin expression, and influence mitochondrial dynamics further broadens its theoretical utility across cancer types.